Welcome to the fourth practical session. Yes, today I'm with Tanja. So next week you'll probably see Michael again. So what do we do today? Well, last time we said we wanted to do something about functions and stack and look how this works. We didn't quite get to that, so we'll do this today at the beginning. Then from last week, the bitwise operators, we'll look at them a bit more, and also arrays.
Yep. So first, let's look at some organizational matters. So for assignment 1, you've already seen that you've been able to register for the assignment interviews since I think 2 days ago. The registration deadline for that is at 6 o'clock today. So if you're looking at this right now and you're thinking you're not registered yet, please do so now. A lot of the slots are already taken. So yeah, please just register through the Teach Center. And if there are any problems with the registration or none of the slots that are left fit you, then please just ask us on Discord. Yeah, then we'll also quickly talk about the interview procedure of the assignment interviews. So basically what's going to happen is you will receive feedback on your code, how many test cases you passed, warnings, deductions, all of that. Then you will be asked 3 theory questions, which will be graded, and one of those questions will always include how to compile your code. And as we've already told you, this does not mean executing make test, but really the entire command that the makefile executes. So please make sure that you know how to do that. And you will be asked questions about your code. So just go through it again, go through the concepts we've discussed in the lecture and the practicals, and you'll be well prepared.
Yes, so we really want to test you that you understood everything that you needed for assignment 1 and that you applied. So the theory questions some will be more in depth, so make sure that everything you use, you also really understand. Yes, and that also already brings us to assignment 2. The introduction video again will be released today at 7. It's similar to the one last time, so everything will be explained about assignment 2. In the video, the most important things are that the deadline is on the 19th of November, again a Wednesday. Again, please start early, push regularly. Virtual machines can crash. They can also corrupt in some way so that you lose some of your progress. And if you push regularly to GitLab, this definitely then won't be a major impact on your progression through the assignment. Yeah, assessment of assignment is the same as in assignment 1, but make sure to follow everything so that you don't get deductions. And again, we have a question hour. It's again on Monday before the deadline, but this time it's from 10:15 to 12:30 in the Hörsaal I7. Yeah, we looked at your calendars and we hope that most of you have time. Okay, so let's start with what we didn't get to last time. Maybe just a quick recap what we did. I'll open it in VS Code. We had this program that read multiple characters from the input and then print out the largest digit. So and then the last version, we had this split up in functions. And if we inspect the main, okay, we have this loop, and we loop until we do not want to receive another input. We had, which depends on this ask for repetition. If we look at this function, this just asks the user if they want to enter another input. And if it's the character Y, then we return true, as you see here. And we also clear the input buffer. So the input buffer was something last time that will be quite important for assignment 2. So I suggest that you watch this again on the input buffer if you still have some conceptual difficulties with this. Then if we loop, we read largest digit, and this directly returns the largest digit. What this does is just empty the input buffer with this loop. So until we reach the end of line that the user entered, and then if it is a valid number and the current character is better than the best character that we have found until now, we'll return this, and then the print largest digit function just prints the largest digit or no digit found if we did not find any digit. And what we want to look at today is how this behaves in the memory of the computer. So first, I want to talk about what is the stack. We want to look at how the variables are laid out in memory. And of course, we can't just put them anywhere in memory. Our program needs to be able to find them again. And what the compiler does is that it stores this somehow in a structured manner in what is called a stack frame. And each stack frame belongs to one function. So all variables of one function are stored in one stack frame. And now why is this called a stack? Well, whenever we call a function, we of course get a new stack frame with all the variables that are in this function. And this is added to this memory that we call a stack. And then when we return from this function, this stack frame belonging to this function is removed again. So you can kind of imagine this like a Stapel in German, where you stack on top if you call a function, and then once you return from one function, you remove that stack frame with all of those variables again. And yeah, that's basically how they are structured. Okay, this was now very theoretical. Let's look at this in practice. So what happens when we start in our main, when we executed this line in our main function? Well, our stack looks something like this. We are in the stack frame of the main function, and we have this variable one more input, and it's currently false because we initialize it like that. Now, what happens if we continue? Well, we immediately enter this loop here, and we call read largest digit. So if we look how this looks, we have this larger digit variable that is not yet initialized, so we do not know what's actually in memory. It could be anything. But then it immediately calls the read largest digit function. And now this is a new stack frame because we enter this read largest digit function. And all of these variables that will be in this function are in this stack frame. And this is the input char and the best char. And right now we are here. So before actually any code function ran, we just called it. And so the input char and the best char is not initialized. But if we, for example, now continue until this printf, then we initialize the input char to 0 and the best char to 47, which was the ASCII code of the character, which was before the 0.
And what happens if we return this function?
Yes. Exactly. Now, for example, let's say we found this best char 50 here. In this loop, we get to the return. What happens? Well, the return, then we return the best char. So the best char is copied back into the stack frame of the main function and saved into the largest digit variable, because that's where we store this here. So as you can see, here we have this copy into the largest digit variable that we have here in the main function. And then once we exit the function, we can also now see that all the memory that we have in this read largest digit function, so the whole stack frame is removed from the stack, and the memory, we shouldn't access this memory anymore. Okay, now so we are in the main, and we call the read largest digit. Now we are here. So what happens if we call a function which takes a parameter? Because the read largest digit did not take a parameter. Well, then in the print largest digit, this parameter here is actually a variable in the stack frame of the print largest digit in the memory, and we copy the parameter to this function. So what's really important here to see is that these two largest digit variables are actually two different variables. if we assign here to this largest digit here, to this parameter, we only change this value. But if we do not return it, and we do not return it because this function has a void return type, then we can actually, if we return here and this stack frame is deleted, we can't access this value again. So then it's basically gone, and this was never modified as it is a completely different variable somewhere else in the memory. So this now might sound easy, but for future concepts that you will learn today in the lecture, it is really important that you understand that this happens, that that a parameter is a new variable that is just copied to this function that we are calling, and it's not the same. Yes, and when we return, of course, the stack frame is destroyed, and I do not know if we have one more image. Yes. Then when we are back in the main function, here we just have, and we printed the largest digit, and because we did not return anything in the main, nothing changed, and yes, we are finished. Are there any questions to that? Okay. And let's close this.
And switch back to the slides.
Yeah, all of these visualizations are also in the slides, so you can go over them afterwards.
Okay, so then we'll next have a look at bitwise operators, which you already heard about last week in the lecture. So to discuss those, we're going to go through a bit of a programming example to see a practical application of them. So what is going to be our goal with this program? We want to read a positive number in decimal representation. So not in the sense of a decimal number, but in the representation of like 5, 10, 12 as we know it. We want to read the input of such a number, and we want to transform it into its 32-bit binary equivalent representation through the use of bitwise operators. And we also want to store this binary representation in an array, so we also cover arrays, which you've also heard about in the lecture. So before we talk about the bitwise operators, we need to repeat a very important concept, which is signed versus unsigned. Because we have signed and unsigned data types in C, and which one we need to use really depends on the context that we want to use a variable in. Because unsigned means that we can only represent positive numbers or 0 with that data type. So for example, if we have an 8-bit unsigned character, the range of that would be 0 to 255, a total of 256 values, which is what we can display with 8 bits. And if we have a 32-bit unsigned int, we can display 0 to 4,294,967,295, which is also just the range that 32 bits can hold. But if we want to do this signed, we also need to consider that we don't just have positive numbers, but we can have positive and negative numbers. So that means this range that we had up here is not just basically split up in equal parts in the negative range as well as the positive range. So we still have 256 values with the 8-bit signed char that we can display, but it's not 0 to 255 anymore, it's minus 128 to 127. Same goes for the 32-bit signed int. I'm not going to read that now, but yeah, you get the point. Now the big question is, which we've also discussed in the lecture already, what if we go over or under these ranges? Because technically nothing is stopping us from just saving -1 into an 8-bit unsigned char, right? Well, what happens is over or underflow, which means if we take our 8-bit unsigned char as our example again, and we look at the binary representation of the highest value it can hold, so that's 255, that would be displayed as all ones in our 8 bits. But if we go to 256, basically what would happen if we could hold more than 8 bits, is that we would put a 1 here as the 9th bit and everything else would be set back to 0. But since we can't display that, we kind of just loop back around and we're just at a 0 again.
Yeah, so kind of how you can imagine this is like with decimal representation. If you add 1 to this, if you want to add 1 here, well, we can't display a 2 because this is binary, so we put this to 0 and carry the 1. The same here, we carry the 1, up until we have the most significant bit. We add the carry here, and this goes to 0, and then we still have a carry of 1, but this carry of 1 just gets lost because we can't store it anywhere because we just have 8-bit, and therefore we set everything to 0 and lost the carry. So we just have 0 now.
And the same also goes for underflow. If we have the binary representation of the lowest number an 8-bit unsigned char can hold, which is 0, we just have all zeros for our 8 bits. But when we then go to -1, we go back to all 1s, and we basically, again, just loop back around, and suddenly we have 255 again. So if we were to assign an unsigned char the value -1, we would have 255, which given the situation is not what we want, so we would need to use a different data type. We would need to use a signed char if we want to display a -1. Yeah, so we discussed that we want to write a program where we can transform a decimal number into its binary representation. So for that, we need to be able to get the bits of this number at each of the positions. So how can we do that with our bit operators? We will show you how to do that with the bitwise and the right bit shift operators. So just to recap what these did, I hope that's not too small to see. If we have a signed integer, a, that holds the value 5. This 5 in binary would be 0101. And again, just as a recap, how you read binary from the right, and we go in multiples of 2. So that means we start with 1. We have a 1 at the position where we would expect the 1. We have a 0 at a position that we would expect the 2. And we have a 1 at the position where we would expect the 4. So that means we basically have 4 plus 1, which is 5. Hope that makes sense. And if we then go ahead and we want to set our value b to the bitwise AND operation of a and just the regular number 1, this is basically the equal of, if we just take our representation of the number 5 again, and the representation of the number 1, which because it's just 1, we just have the rightmost bit set to 1. A logical AND operation works in this way, that only if the bits at the same positions at both sides of the operation are 1, then we return a 1. If only one of them is a 1, or both of them are 0, then we return a 0. So in this case, if we look at the first position, we have a 1. We look at the other first position, we also have a 1. That turns into a 1 over here. Then for the second one, we have a 0. Here for the second one, we also have a 0. We return a 0. For the third one, we have a 0 and a 1. That's only one of them set, so that means we also return 0. So basically what this result would be, we would set the value b to just the decimal number 1 through this.
Yes.
I hope that makes sense.
And maybe we should now observe that here with this AND operation, it's basically just if we only have this one in the rightmost position, and if we look at this here, we get as output a 1 if this is a 1, and if this is a 0, we get a 0. So we kind of extract just what is the position of the first bit of this A.
Exactly. And to then continue with the bit shift right, we set a value C to the operation A right shifted by 1. The right shift in this case can be taken quite literally, because we have these positions here. Then we right shift it by 1, and you can really just imagine that the rightmost number just goes off screen, sort of. So if here we have 0, 1, 0, 1, this one here just gets cut off, and we're left with the 3 positions that we had, technically 2, because we wouldn't have to display this 0 quite here. So the only significant bits that we're left with would be 0, 0, 1, 0. So we would transform what used to be a 5 into a 2. And that would be the value that C holds. So we're really just shifting the entire binary number by the number of positions that we have next to the bit shift operator.
Yeah, and with those 2 concepts, you could imagine how to get every position of a binary number and extract what if the bit is set there or not.
Exactly. So then let's get to the live coding. So we will start with our little program. I've already put a functions header here that we want to include in this. So what we said is, okay, first of all, we want to read in a decimal number. We don't really have to think about this that much anymore because we've done this a lot of times in the practical. So we write ourselves a small little function called read decimal input, which will just hold a void because we don't want any parameters here, we don't need any. And we will return an unsigned integer here because we said we only want our program to be able to do this, to transform the decimal number into the binary representation for positive numbers. So we don't want to read in anything that's negative, so we will define an unsigned integer as the return value of this function. So since we said we want to read in an unsigned integer, we will also create a variable that will hold this called decimal number, which we'll just set to 0 for now. Then we'll include a small little print, which is just going to say enter decimal number so we know what is expected in terms of input. Then we will wait for the input of the user. We've also seen 2 ways to do this. In this case, we will use a scanf. And careful here, we have a format specifier specifically for unsigned ints, which is %u. Then we can continue as before, address of operator, the variable we want to save this in. This is how we read in, oh, I forgot the thing here. Right, so this is how we read in our unsigned integer into our decimal number variable, and all we now need to do is to return it. And that's how we handle our input. Now we also need to call this in here. We'll just also create an unsigned integer here because that's what we're expecting. We can also just call this decimal number and then call our function, which doesn't take any parameters. Exactly. So we can just have a look at that real quick. We go to the terminal. Oh, this was the one. Already executed that before. There we go. So now we just have our compile command again. What's our warning? Oh yeah, because it's not used. And there's no new line at the end of the file. But that's fine for now. And then we can just execute that real quick. Then we have the enter decimal number. And we enter 10. Nothing happens yet, but we're already reading it in. Okay, so now the interesting part starts because we want to create a function that gets us the binary representation. So we will first define the overarching function for that before we get the separate bits out of our decimal number. So since we need to keep track of kind of where we are in the number, because we've seen that, for example, 5 is displayed as, if we look at it from the right, 1, 0, 1. So we do have different positions here. We have like a number at the index 0, one at the index 1, one at the index 2, and we need to extract those one by one now. So that means we need to keep track of some type of index, which we also need a variable for. This index should also not be negative. We don't want it to be negative, so we can also use an unsigned integer here. And we can just call that bit index for now. And we set that to 0.
So this tells us if you want like the first bit or the second bit or the third bit. Yeah.
And then we will define our current bit, which is the return value that we want to get from the function that we will ask for, please give us the third bit, the fifth bit, etc. And we will use a signed integer here. We haven't explicitly mentioned this, but if you just put int as the data type of a variable, that means it is signed automatically. If you want it to be unsigned, you really need to explicitly put this unsigned int here. For A1, this wasn't that relevant yet, I would argue, but possibly for further assignments, it will be important that you think about the types of values that you want a variable to take. Right. So now we want to call our function for getIFBit, which we will still write. We will do that first. So we're not done here yet, but let's put a 0 here for now. So this function will take our bit index, which we need to determine where we are in the number, which bit we want to extract, and the decimal number itself. So what we need to do here, as we've said, we can extract a bit with the bitwise AND operator if we just use the bitwise AND with a 1, if the index we want is to the very right of the number. But if we want the fifth index, for example, that's not the most right place of the number, right? So what we need to do is we need to shift our decimal number 5 positions to the right, then use the bitwise AND operation, and that way we can extract the bit. So we can do this by just setting our decimal number to the decimal number, shift it to the right by the bit index that we've passed here as a parameter. Now we could run into the case if, for example, if we take our value 5 again, it doesn't really make much sense to, for example, shift by 5 positions because we've established that the number 5 in binary can be represented by, if you look at it from the right, 1, 0, 1. That's only 3 positions. So if we shift to the right by 5 positions, that doesn't really make much sense because, yeah, the number is already over. So that means we can add a check here for if our decimal number equals 0. Because if we shift this too far, all we're left with is basically just zeros behind it. So this is why we check for that. And what also doesn't make much sense, we've said before that we only want to look at the 32-bit binary representation. So it also doesn't make much sense to shift more than 31 positions because, yeah, the number is over by that point. So that means we can also add a check here for if our bit index is bigger or equal 32. If one of these two cases happens, that means we just return -1 because as a kind of indicator, we're done. We don't need to continue. We have our binary representation. And this is why it's also important that we set the return value of this function to a signed integer, because this wouldn't work if we put an unsigned int here.
Yeah, so this -1 is like error code or a code just so that we know that we are finished with getting all the bits of the number, because if we try to look at the 6th bit, for example, and all ones of this number already were to the right of that bit, we know that there are only zeros left that we will ever read. Therefore, we can just stop because the leading zeros in the number, of course, don't change the number. This is the same as in decimals. So, for example, if you have 12, it's the same as 0, 1, 2. If you just put leading zeros there, then you don't change the number.
Exactly. And then, so what we've done now up here is we've shifted our number to the right by the amount of positions of the index that we want to look at. So if we wanted to look at the 5th position, of our decimal numbers binary. We have shifted it 5 positions to the right, which means sort of the index 0 is now the exact bit that we want to look at and that we want to extract. So what we can do now, since we've heard we can extract the bit with the bitwise AND operator, we can just directly apply this to the decimal number, since we've set it anew up here after the bit shift to the right. And we can just do AND 1, and we can immediately make that the return value. Now, quick question to the crowd. Does this influence the decimal number we have in the other function? Who thinks yes?
So we assign the decimal number here, up here in this line. But we passed in the decimal number from the get binary representation. Yeah. So does this in any way change the decimal number we have in the get binary representation or in the main? So yeah, who thinks yes? Who thinks no? Okay, so most of you voted for no, so I hope what I explained earlier, you understood that, because yes, of course, this is copied again, so this won't change anything. Maybe should I draw this shifting and the end on the blackboard? Maybe we could look at it.
Yeah, we could have a look at that, yeah. Do we have chalk is the question?
Yeah.
Okay, we have
maybe
chalk.
Just, if we stick to our previous example, if we just have some binary representation like that, and for example, we want to check this bit here. This is at index 2, so index 0, index 1, index 2. And then the first thing that we do is we shift it to the right to the index we want to get to. So this index 0, okay, you can't read that. We shift it to the right by 2. So what this does is it shifts this 2 times over. So what we are left with is just the 0 and the 1, because we cut off this part here. Because we shifted it over by 2. And the next thing is we do with this AND 1 is we just do the bitwise AND with the 1, and so like this, 0, 0, 0, 1, 1 is 1. And now we know that at this position here, our binary number was actually a 1. Yeah.
Right, so we now have a way to return the bit at some random position I with the help of our bit index and the decimal number. So now we can continue down here. We did say that our signal, so to speak, for stopping or for noticing we're done with creating our binary representation is the return value -1. So that means we can use that as a loop condition, because of course we want to call our getIF bit function multiple times. So we'll do the first call up here and give that our bit index variable and our decimal number in the get binary representation function. And then we want to loop with, for example, a while loop, while our current bit, which is the variable that takes the return from the getIF bit function, while this is bigger or equal 0. You could also write it while it's 1 or 0. It doesn't really matter. The point is that the -1 return value shouldn't make this condition true.
Yeah, or while it's not equal to -1.
Yeah, that also works, yeah. So then, since we already got the bit from our initial bit index, we can continue by increasing the bit index, since we want to keep looping until we're done, right? And we can just, once again, always set the current bit to the return value of the getIF bit function, and we will just keep passing the bit index and the decimal number in there. And as a final thing for the first step, we will also have a print here, which will just tell us the current bit is %d here again, because we've set current bit to assigned integer. And that will be our current bit. Let's add a new line here so it doesn't look as terrible. Right, and now we also still need to, we did all this in the get binary representation function. We still need to call this in the main, of course. So all we've done so far is just read in the decimal number here. So we can just call get binary representation here and pass it the decimal number. And with that, the program should already show us some results. So we'll compile once again, execute it, and let's do the number 5 that we've been talking about this entire time. And we have 3 bits. Current bit is 1, 0, 1. So with 5, we can already see the correct representation. You may notice something if we, for example, enter, let's do 10. We may notice something here. Because if we think about it, what would the number 10 be? So if we have 10, we have once again, we have like the position. At the first index, we have what would be a 1. Then we have what would be a 2, what would be a 4, and what would be an 8. So if we want to have a 10, that means we would have 0, 1, 0, 1. So 8 and 2, that's a 10. So we have from the right 0, 1, 0, 1. So if we look at the program output now, we may notice that the first place here, the 0, is the rightmost position. So there's something we need to be careful of here, because we said we want to save this in an array. Because in an array, we don't start from the right, we start from the left usually. So what we do need to do is we need to either flip the array or we need to flip the print we do of the array. That's something to be careful of, because with binary numbers, you always look at them from the right, from the least significant bit to the most significant bit, but that doesn't really align with how we usually view decimal numbers. So do be aware of that if you need binary numbers at any point, that this is a difference to consider.
Yes, and it also just comes from us starting at bit index 0, which is at the right, and counting up, and then, yeah, that's the order it is printed in. Okay, but we said we also wanted to do something with arrays, so let's try saving this into an array. Okay, so I think I'll just create an array up here. And yeah, let's call it binary. Binary representation. And now we want to store each bit, which is just 0 or 1, into this array, and we want to store all 32 bits. And what I'll do now is I'll just write this. This sets the whole array to 0. Because here we stop looping once there are no more ones left, but then if we do not set the array to 0 here, there might be some garbage data in the upper bits. So this is again a situation where initializing the variable is important, because it might not be now so easy to see here that we are not overwriting the whole array. Yes, and now instead of printing it, I'll just write the at the bit index, write the current bit. Or let's say I'll do this. Yeah, let's say I'll do this instead of printing. Okay, so now at array index 0, there is the least significant bit of the binary number, so the one to the right of the binary number. And as you said before, now we need to be careful, because in the array, we now start at position 0, the least significant bit. So if we have 10 here, actually in our array at position 0 is this here. So if we now loop through our array, we again would get something like this. So we need to start at the very top. And to do this, we'll also use size of again. So I'll call this, okay, we already have bit index. Yeah, I'll call this binary representation index. And okay, so how do we get the length? Well, we know it's 32, and now I could just use 32 again. Then I would need to declare a constant, so we could just set define constant, the length that we want here. But just to recap size of, how do we get the size of an array? Well, first, of course, we need to do size of binary representation. Are we done now? Yes? Exactly. So what we need to do here is divide by the size of one element in this binary representation.
Quick question in the middle. Why can we just say size of int here? Would it make a difference if we said size of unsigned int? I already heard something, but let's do hands up. Who thinks yes? Who thinks no? The no people are correct because a signed and unsigned integer are both 8 bits long. So that means it actually doesn't make a difference, even if we would be talking about an array of unsigned integers here, whether you do size of int or size of unsigned int, because they're the same size.
Yeah, and because you want to use this as an index, and I hope that you understand that if you have an array of length 10, as we start with 0, the highest index is 9. So it's the length minus 1. Because we start at 0. We need to subtract 1 from the length, because else we would be out of bounds. Yes, I'll just continue in the next line. And now we want to loop up until the last bit, so up until our binary representation index is still bigger than 0. And we also want to increase the binary representation. No, we want to decrease the binary representation index. Yes, so what we do here is that we go from the highest index, which is 1 minus the length minus 1, to the lowest index, which is 0. So, and here we need bigger equal, because we still want one loop iteration for when this index is 0, else we would skip that.
Yeah, so this is basically also just the exact opposite of what you would usually do in a for loop. If you have an upper bound that you don't want to reach, we always say smaller than the upper bound, and bigger or equal is just the exact opposite of that.
Yeah, and now I'll just print this here like this, and then afterwards I'll print some new line character so we don't get each of those 32 bits in a separate line. Okay, then I think we can try this. Let's try it with 5. And yeah, this seems already correct. And you can also see that we really got the looping correct, because all of the zeros that we have here that fill up this whole 32-bit are on the left. If we would have mixed this up with the array, then this would be exactly inverted. Maybe let's also try 10. And yeah, we can also see we have this 1, 0, 1, 0 here.
And we can also try like a bigger one, maybe like 4 million or something. 4 billion or how many?
You need to run the program again.
So now we have 4 billion. And we also get the binary representation of that. And by this, we can already see, since we also have set the bit over here, that we can indeed represent 32-bit binary decimal numbers as their binary representation, because we've used all of the bits we can to the left. Yeah.
Yes. One more thing about this example is we talked about the stack now today at the beginning, but how does an array look on the stack? Well, let's see. We call here in the main, for example, with the decimal number 1, 2, 3, the get binary representation function, and the decimal number, as you all said, is copied to the get binary representation. I also wrote the code here. And now we have this integer array binary representation, which has 32 members or elements. So what happens on the stack is that the single variable binary representation now lies as one big block of memory on the stack. And why did I draw it like this? That the 0 is at the bottom here and the 31 is on top here. Well, there's one detail about the stack, namely that in the memory of your computer, the stack grows as we've drawn it here from the top to the bottom. So in the last lecture, you heard about memory addresses at the very end, I think. Yeah. And there, and now we can see that in the stack, the high address of the memory is at the very top, and it gets lower and lower, but the array is still from a lower address to a higher address in the memory. This might be a bit confusing now, but hopefully it gets clearer with today's lecture. But yeah, just now, for now you can just accept it, but this is important that actually in the memory, the array, like the stack grows from top to bottom, and here the array but still goes from bottom to top. Yeah, and as we can see here, the index that is the highest one is 31, so we have 32 elements because we have 0, 2.
Are there any questions on that? Doesn't look like it.
Okay, then, yeah, let's continue with our last topic. So we'll just talk about 2D arrays. Yeah, we are already in the live coding. What is our goal? This will be a very, very short program just to illustrate how 2D arrays work. And what we'll do, I just want to store the current temperature measurements in a 2D array. And the first row of the array will be day 1, the second row will be day 2, the third row will be day 3, etc. So I'll need to specify how many measurements I want to take each day and how many days there are. So I'll make constant for that. So first number of days, let's say 3. Measurements per day, let's say 4. And now, yeah, what we want to do in this array here is that we want to store in the rows the measurements of the day and more or less the
rows, you mean?
Yeah, so the rows, if you go along one row of the 2D array, it will be the measurements of one day, and if you go to the next row, you will have the next measurements. So the columns are the measurements. So we will have the number of days here and the measurements per day here. So maybe this is now a bit clearer. So the outer dimension is the number of days, and the inner one are the measurements. And now we can also do this with an initializer list. And what we'll do is so we have like 4 measurements on the first day. Then on the second day, we also have some measurements. And on the third day, we also have some measurements. So now maybe it's a bit more clear what I tried to say earlier. These are the days. So one row is 1 day. And in each row, these are the 4 measurements that we took each day. So for example, this year is Monday, we took 4 measurements. This year is Tuesday, we took 4 measurements, and so on.
And if we want to loop over that now, because we want to print our weather measurements or our temperature measurements to do something else with them, to display them somewhere, we also make use of these 2 dimensions that we've specified here. So we'll first use a for loop, and we will call our helper variable day, because we start with the outer dimension, as we've said, because the outer dimension is the 3 days, so that would be the rows. So we make that 0. Then we want this to be smaller than our number of days, and we'll increase it. And then we can first start off by just printing like a little prefix to this, to all of the measurements, so we see which day we're on. So we can do something like day %d, and then we'll just put the day here. But we will say day +1, because once again, whoopsie, misclick. Because we're using the day variable up here as our helper for indexing. So that means if we have 3 days, as we've specified, that means we will go from index 0 to 1 and 2. But that also means we would say on day 0, the measurements are this and this, and that doesn't really make that much sense displaying it when a human reads it, so that's why we're doing day +1 here. And to actually print our measurements then, we will use the second dimension that we've had up here, which are the measurements per day. And we will once again use a for loop, just call that measurement. Whoops. And that is again smaller than our specified constant. We will increase it to loop through it. And all we need to do then is to make a print statement with %d, since all of these are integers and we have an integer array. And we just add a comma here. And we will then use our array with exactly the 2 helper variables we've defined for each dimension. So first, we always said we have the rows as the number of days. The outer for loop is also for the day, and we will also use day in here to kind of get to the row that we want to get to. So if day is 1, for example, we start here at this row at the first position, which would be the 8. And then we jump further ahead to our second dimension, which is the measurement helper variable we have here, which if that is 2, for example, then from this 8, we would jump 1, 2 positions to 12. In this case, we loop through all of them, but just as a little explanation so you understand the concept. And then we also want for each of the days for them to be printed in separate lines. So we'll also add a printf for a new line down here. So we have a basic way of printing our array. Well, should be a bit further up. There we go. Okay, and that looks good. We have 12, 14, 13, 8. That's our first row, our second row, and our third row. There's also another way we can print this now.
Can I do the
yeah, of course.
visualization? Yeah. So let's talk about the visualization, because how does this look now on the stack? you might ask yourself, because we have seen how one-dimensional arrays look on the stack, how do these two-dimensional arrays look on the stack? And well, they look very similar to the one-dimensional ones, just that the whole array is one big block of memory in sequence on the stack. And if we look at the indices here, I hope you can read them. We start at the index 0 at the bottom, so both 0, and then we first increase the inner dimension. So here are the measurements that we increase. So we go from 0, 0 to 0, 1 to 0, 2 to 0, 3. So up until here, to this 8 are all the 4 measurements that we did on the first day. So on Monday, for example. Then the next 4 here, we have index 1 for the day, and then 0 to 3 in the second dimension. Okay, but I don't know if you heard this in the lecture, but there's one thing we can do when initializing an array like this. Namely that we can
you need to switch
yeah,
back to.
we can leave out the outer dimension, so the number of days for this array here. So I comment this out. Maybe I can also delete this to make my point a bit clearer. We can do this and our code still compiles. But how does this work that we can just leave out a dimension and the compiler still knows how to correctly index into this array? If we go back to the visualization now, what do we need to do if we want to access this element here? So this 13, for example. We say, okay, we want to go to day 1, measurement 2. How do we actually get that we go to this 13 here? And we only know that our temperature starts here. So 1, 2, 3, 4, 5, 6. This is like the 7th element in our array at index 6, because we start at 0. So this is at index 6 in our array. If this were a one-dimensional array, how does the compiler actually get to this when we type this? And the only thing that it needs to know is how many measurements there are in one day. Because if we say here that we want to go to index 2 in day 1, it knows, okay, in day 0, there were 4 measurements, so we'll skip 4 and then just go to the second index on the second day. I'm explaining this now because this is very related to the concept you'll hear in the lecture today. Yeah, maybe just to show you that this is actually what happens. Should I type it, or do you want
I can do it. I can do it. So we'll just basically do the same as up here, but with the concept that we've just heard. So we want to, once again,
we'll more or less kind of do a trick now in the compiler. I'm not sure if this one is 100% legal, but we'll do it now.
So we want to once again take our temperature array, but we've said we don't care about the first dimension. We don't need that to actually get to the index that we want to reach or to loop through the entire thing. The only thing we need to do now, as we've said, we need to know how many measurements per day. So the second dimension we actually have in order to get to where we need to go. So we know that one row like this is 4 elements long because those are the measurements. So if we now just take the loop variable we have here, our day, so like are we on day 0, day 1, day 2, and we multiply that by our measurements per day. So for example, if day would be 1 in this case, this would go 1 times 4 positions forward from the first one. So that would be, if we're at 12 here, we go 1, 2, 3, 4, and we would start in the second row again, just like if we put day in the front here. That is basically the same thing in this case. And then if we, for example, want to get to whatever offset we are in the second row, we just need to add our measurement variable, which was the helper variable for the second for loop that we have for the inner dimension. And this will do exactly the same thing as the line we've commented out up here with the axis where we use both dimensions. This will do the exact same thing.
If you're having trouble while we're writing 0 here for the outer dimension, just ignore it now and pretend that we are treating our two-dimensional array in the stack like a one-dimensional array. So we're just now treating this two-dimensional array like a one-dimensional array, and we're doing these calculations to get to the correct index.
So if we then execute the program again, we once again have the same correct prints as we've had before of the first row, the second row, and the third row. So these are just two different ways how you can jump through a two-dimensional array. One is the way that you treat it like a two-dimensional array in that sense, and the other one is our hacky, tricky kind of way where we just pretend that we're not in a two-dimensional array at all.
So don't use the second approach, and please don't use it at the assignment. This now is just for demonstrational purposes, so you can actually see in the code that this really is laid out in the memory like a one-dimensional array, just that the compiler now knows additionally how big the inner dimension is, so that it can, if we index the outer dimension, it knows how many elements to skip to get to the correct day. And now we can also explain here why we just need the inner dimension, because when we calculate our index, similar to maybe how the compiler would do it, we also just need to know what is the inner dimension of this array, and we already get to the correct element.
Are there any questions on that? Doesn't look like it.
Yeah, if there are no questions, because now you are just, I don't know, overwhelmed and it does not make any sense what we do here, then maybe wait for the lecture today and it'll get a bit more clear. We'll use very similar concepts in the future. That's why we just wanted this to show now to prepare you for things. So what did we do today? Well, first I talked about the functions and the stack from last time.
Then we talked about the bitwise operator example and how we can transform a decimal number into its binary representation.
Yeah, and finally, again, with the temperature, the 2D array now. If for the 2D array, the calculation we did does not make any sense, maybe you can look at the visualization again as a homework and just try to come up with a way of how to get to the correct index in a one-dimensional array. And if you think about this, you should arrive at the same calculation as we did. Are there any more questions to anything we did today? When do you want to start with the lecture? Because now we're finished 10 minutes early. Okay, so at 50, so
in 14 minutes?
Yeah, in 14 minutes we will start with the lecture. And yeah, then see you next week.
And think of registering for the assignment interview if you're not yet.
Don't forget this.
You have 1 hour and 14 minutes.
If you're not registered for the assignment interview, you can panic a bit now because you really need to register. Okay, then until next week.